Hi everyone. So in this video I've performed a measurement, a passive measurement on an RF filter, and I feel like I ran through it a little too quickly without slowing down and showing some of the practical details of what the measurement kind of meant. With regard to the traces, the scales, the pass band and stop band goals. Basically, why would one measure this filter for the purposes of putting it in their system, and what goals, what results you'd want to pay attention to when measuring the filter. So what I did here was I printed out a response plot of a spec sheet, or from a spec sheet of a filter online, and I'm going to go through the particulars of the marker settings that were done here and the scales of each trace, just to kind of bolster the information that I provided later in this video, where you actually just plug the unit into the network analyzer and made the measurements. So I have this plot of this filter I printed out, and I want to illustrate if speccing this filter out in a system and using it, what you'd want to understand about it, and what the pass band, stop band goals are of just a filter in general. I mean, every system has its different requirements, but they all have similar needs as far as when you're transmitting at a given frequency or in a given band of frequencies, you don't want to interfere with things that are out of your channel. It could be another transmitter in another channel, or it could be even your receiver if you're receiving on a different band. So we'll use this plot to illustrate what we're looking at here in the following measurements that we're going to be making on the network analyzer. So again, let me preface this by saying this filter is a 700 meg filter. We were testing a 2 gig filter, but all of these concepts kind of stay the same as far as you're transmitting on a given band and you want to keep your radiation, you want to keep your anything else your system's going to be doing in these other bands out of it. So with the markers that have been set here, we have a marker set at marker 1, which is 715 megs, and another marker which is at 757 megs. So this you would consider the pass band of your filter. I'll just put PB here. And any of these areas on this side of the filter, you'd consider your stop bands, or areas that you would not want to be radiating in. Now, this plot is slightly different than the plots that you'll see in the later part of this video, just by way of setting up the analyzer. In the video you'll see, or in the later part of this video that you'll see, I have split the S11 input return loss plot and the S21, a little bit redundant because I talk about it in the later part of the video. The input return loss, the amount of reflection that occurs on the input port of the filter, is very low in the pass band of the filter because it is sending it out of its output port. But in the bands that it is trying to reject, it is more or less reflecting all of those frequencies completely back into the source, because it's serving its function. It's allowing 715 to 757 megs to go through, and not allowing anything close to out of that band to pass through the filter. So in another way of showing this is with the gain plot, or the S21 plot, where you have very low loss in the passband, but very high loss in bands outside of the filter. So if we look at this plot in a little more detail, we can see that markers 1 and 2 over here show a loss of about 6 to 7/10 of a dB across the band that the filter wants to pass through, or the filter is designed to pass through. And the manufacturer here has given us two kind of reference points at marker 3 and 4, which are here and here at 685 and 778 megs, 685 and 778 megs, to show us by how much this filter will reject at these two bands. So at the 685 meg band, or 685 meg frequency, the filter is attenuating, with regard to this reference line over here, the signal by 54 dB, which is a lot. 60 dB is a factor of 1,000. And at 778, 56 dB, which is fairly high rejection as well. So for purposes of this filter, if you're going to use it at 736 megs, which is its center frequency, you can count on it being able to reject frequencies beyond 780 megs very highly, 60 dB or more. And that will guide your decision in picking a filter, where you're given a system and the people doing the link budgets say, hey, we have a receiver in this area right here. So anything coming out of this transmitter needs to be really, really, really knocked down so that we don't interfere with the receiver in this band right here. So that's kind of the practical considerations when selecting a filter. And in your day-to-day, if you're an RF engineer, you're going to be looking at a lot of filter plots, a lot of different types, topologies of filters based on the power level that you're working with, based on the channel conditions, based on regulatory requirements, because sometimes you're going to have to operate a transmitter in a certain band, and the FCC or the ETSI or some regulatory body is going to say you cannot have transmissions above X amount of RF power in the bands you're not working with. So this is how you would look at, interpret, and measure your filtering products to get an idea of how you're designing the system and what filters you need. Basic goals for every filter is, ideally you want the minimum loss across the band you're going to be transmitting, and the maximum loss in the bands you're going to not be transmitting in. Of course, there's a multitude of trade-offs regarding loss versus size of the filter, amount of rejection versus size of the filter, and a bunch of stuff that has to be juggled when you're designing your system. So I hope this provided a little bit more insight on the actual measurements that were being displayed on the network analyzer, because I didn't go through that kind of stuff in very much detail. So we're back with a new video, and in this one we're going to kind of follow on to the open short load through calibration that we performed on the 8720 ET, and just look at a simple measurement of a passive device. So we'll be measuring two cavity filters here, the K&L microwave comb line, and then another pretty old one from Mytech, just another cavity filter. This one's about 4 gigs center frequency. This one, from what I remember, is around 2 gigs. So we have our setup. It's been pre-calibrated already with a method more or less exactly the same as was done in the cal video. I do have now a little better cal kit. It's from a company called Withwave, and the difference between this one and what we were using in the last video, these rings, or these ones on the ring, is this one comes with calibration data that can be incorporated into the network analyzer. Haven't done that for this, but in general it's a higher quality kit with a much better 50 ohm load. So how do we know that we've calibrated this correctly? Well, with our input connector open, we're seeing 0 dB return loss across the band. That's a good indication, but another way to kind of verify that is we're going to hook the port 1 up to the load. As you can see, the input return loss drops to very low levels. When I fully screw this on, we're at about 60 dB of return loss, which means this load is absorbing more or less all of the incident signal. There's nothing reflected back, and we're accurately measuring this because you'll have to take my word for it that I calibrated this. But that's a quick kind of sanity check. Another way to sanity check your cal is to, let me unscrew this, is to reconnect your through and look at your S21, your gain measurement. So now that I've connected the through to the port 1 and port 2, you can see we're registering 0 gain. It's or 0 gain, 0 loss. It's just a through, and we've calibrated everything up to basically these 2 points because, as I explained before, purpose of the calibration is to take all this cabling, all these adapters out of the equation so that when you're measuring the filter between these 2 connectors, that's what you're measuring. So in addition to the bandwidth that I talked about and setting your markers, the scale of each channel has to be taken into consideration. Right now I'm set for 10 dB per division, so each of these rectangular markers, graticules, the space in between each is 10 dB. You can set it for lower, 5 to 1, we'll see the effects of that later, or higher, I think up to like 50, 100 dB. Well, 100's a little excessive, but again, it has to do with the dynamic range of the network analyzer. but you can set it up to a very high level. So when calibrating before and going over the marker settings, another thing to be aware of when knowing what you want to measure here is your scale, your vertical scale. Right now it's set to 10 dB per division. So each of these graticules, each of these rectangles, the distance between the top and bottom of one rectangle is 10 dB. You can set it to a lesser value or a higher value. I can go up to 5, 10, 20, 100. But it all depends on what you want to measure. I've also moved the reference line up here, not in the center, because this is a passive device. It has no gain. So we're really not going to be measuring any part of this line. This line is not going to go up because the filter does not generate any gain, or does not have any gain. It only has loss and then rejection. So moving your reference line up from the center gives you a little bit more range here in making measurements and understanding what's going on with the filter. So like I said before, this is a bandpass filter, so it will allow certain frequencies to pass and block others. So let's see how that visually looks here. So the filter is input connected. I'm going to screw on the output now. And you'll see the trace, the data trace, come up. Now we're connected. With this being our reference line for 0 dB of gain or loss, you can see the filter's general shape here. 2.5 gig center frequency. We have about 0.3 of a dB of loss, which is pretty good. And the center frequency is 2.25. And I've set markers 1 and 3 to the 3 dB points, which is the point at which the filter's response starts to roll off by 3 dB. That's a common way to specify filters. Sometimes they're specified at the 1 dB points, where the edges of the band roll off by 1 dB. But usually it's the 3 dB points. So you can see the bandwidth of this filter starts at 1.87 gigs, stops at 2.56 gigs, which is more or less the usable band of this filter. And I say that with some caution, because at the 3 dB points you are at half the power out. So the actual usable band is more within this center area. So looking at the input return loss plot versus the gain plot, you can see in the center of the band we have an input return loss of -16, which is pretty good, and serves the filter's function. It's logical. The filter will have good return loss in the center of the band, in the bands or in the frequencies it's going to pass, and have a really bad return loss at frequencies it's going to block. So if we play with the scale on channel 2, you'll be able to get a little different information from different scales. We're at 10 dB per division here now. Can't really see what's going on in band, but you can get a pretty good idea of what's happening out of band. If I'll pick another marker, I'll add another marker, marker 4. It shows up here. So let's say you're using this filter at 2.5 gigs, where you have nice, 0.3 of loss, and you want to see how far does this filter reject? How good is it at rejecting frequencies, or 3 gigs? So with our marker 4 at 3 gigs, we can see it is rejecting any frequencies going through it, or sorry, any 3 gig signals going through it by 59 dB relative to the passband. That's a fairly good filter. And if we go out further, we're at about 70 dB at 3.17. And down here we're introducing some measurement error, which we can go over in another video. Same goes for frequencies outside the passband that are below the passband. 1.4 gigs, 60 dB rejection. So that would give you the higher scale per divisions, give you kind of a big picture look at how the filter is performing. If you want to get really granular into the passband, you can lower the scale per division. And as you can see, as we do that, these get steeper and fall out of our ability to view them. But you get a little more detail in the passband. We're at a half dB per div now. So you can see that the flatness across the passband is pretty darn good. So now that this graticule's height is a half dB, we're within, tenths of a dB across this band, which will matter if you're using highly modulated signals. Inter-channel flatness is important for the system to work correctly. Now, for the S11, we're sitting at 10 dB still, because there's, at this point there's no real good reason to see exactly how the input return loss is performing. We just kind of know on a very high, kind of non-granular, very rough level, okay, it's about 20. It's pretty good. It's 15 to 20 in the passband, which will serve this filter's purposes nicely. And if we go to a higher scale per division, you can see this tapers off at 500 megs and 4 gigs. There is some measurement error here because it's rejecting so much that the stimulus in here is getting attenuated too much on the output for this to detect correctly. There's methods to clean that up with booster amps and such. It's more advanced. And basically that's it. We're seeing how this filter is working from 500 megs to 4 gigs. We can probably go over this in a filter specific video, but it's not it's not safe to assume that this rejection is going to get better and better as you go lower in frequency and as you go higher in frequency. It doesn't go, the rejection is not infinite across the band. We'll do some measurements on more advanced measurements on a filter where we can see an even broader band, and you'll be able to see what happens, very far out of band. There's things called comebacks and other things where you really can't expect the filter to filter very, very far out of band for certain designs. And one last point I forgot to mention. This filter is connected directly to ports 1 and port 2 of the network analyzer. Why is that? Because it's a passive device. It doesn't generate any power. When there's a limit to how much the network analyzer can accept, how much RF power it can accept into port 2, which on most pieces of gear it's about a watt, sometimes it's a half a watt. So if testing small amplifiers or passive filters, you don't really need to protect the port 2 of the analyzer, but in a upcoming video we're going to test some active devices, and you'll see how we set up and calibrate for something that's actually going to generate a significant amount of RF power. So thank you for watching, and I'll do the other filter in another video, and we'll get into some more advanced active measurements as time goes on.